So we're going to move on to the final application of spectral techniques in computer science. This is within image compression. Now, this is going to be the final technical lecture of the module, and no doubt some of you may be feeling after the previous 20 or so lectures that there is indeed nothing quite so terrifying as the results of education. So this is a quote from a famous Japanese writer in a newspaper serial that he wrote called I Am a Cat. Okay, so what's our motivating problem here? You've just taken a photograph using, say, some kind of smartphone or tablet device or something similar. And you're so pleased with this that you want to share it with a lot of people. So you decide to send it around as an attachment to a message. But there's a problem. This is so large that you very quickly reach the end of your data allowance. So, what can you do? Well, there are a few options. You could wait until your data allowance is renewed. But we live in a society of instant gratification, and no one wants to wait for anything. You could pay for additional allowance. Better still, you could find someone to pay for you. One option. Very similar sort of approach. You send the image to one person and you ask them to use up their data allowance in forwarding it to other people. And finally, you could just forget about circulating the photograph you've taken altogether. Well, as I said, this is an age of instant gratification. No one is going to want to forget about doing something that they actually want to do. There is another alternative. You could take your image and you could try to make it much smaller. In other words, you want to describe the content but using far less space than the actual photograph occupies itself. Now this seems like a rather strange demand, and in some ways a rather unrealistic demand. So I'm going to be talking about, in this lecture, how we can achieve that aim using spectral methods to help. So how do we do this? Well, first of all, let's look at what an image file actually is. And it's just a table. It's a matrix of numbers. In other words, when we consider images in a computing context, we're dealing with something that is some number of rows, the height of the image. It is some number of columns, the width of the image, and the value in any given row and column. That's just describing the color that that particular pixel should take when the image is displayed. So here's an example, a photograph of a still life painting. And if we look at the details for that photograph, we find it is 388 rows and it is 504 columns. The way in which the colors are encoding, we use 24 bits to encode the color of any pixel, and that's in one of the standard color encoding schemes, the so-called RGB scheme. The total space we take up when we combine this, this, and this is roughly half a megabyte. Suppose we want to use much less space, say roughly a fifth as much, so taking a tenth of a megabyte rather than half a megabyte. Is it possible to do this without losing too much of the image quality, without losing too much detail? So the way we're going to do that is by exploiting spectral techniques, some methods we've been looking at over the past 3 lectures. So to start off with, we have our image. We've seen we can think of it as a number of rows and a number of columns, and we're going to describe that image as a matrix of numbers. Now, one difference from some of the previous examples we've looked at is this matrix in general, it's not going to be a square matrix. The number of rows and the number of columns are going to be different typically. But this doesn't matter. This is completely unimportant. The techniques we're describing can be applied to any matrix. The key result that we need is the following one. If we take any matrix, we can describe that matrix as a result of multiplying as a product of 3 other matrices. The first of these has the same dimensions as our original matrix. The second and the third are square matrices, and their dimensions are the width of our original image, the number of columns in our matrix. And the key property we need is that we can recover our original matrix by multiplying the first by the second by the third of the 3 matrices we've formed. So these 3 matrices, first of all, there seems to be an immediate problem with them. We seem to be using more space than we were using with our original matrix, the one we're trying to compress. Originally, we had an image with a certain height and a certain width. And now we are taking up not only that original space, but the result of adding 2 square matrices to that. So we're taking more space. Now, in fact, we don't use those 3 matrices as they're originally formed. We have to carry out some manipulation with the middle matrix in our 3. So what do we do with that? What we do is we try and throw away some of the entries in our middle matrix. And if we do that, if we throw away some rows and columns in our square matrix in the middle, then there are 3 consequences. We have the obvious consequence that the amount of space this matrix needs is much less. However, we're carrying out a matrix multiplication. So if we throw away rows in this matrix, then we are forced also to throw away columns in our first matrix. And if we throw away columns in our middle matrix, we're forced to throw away rows in our last matrix. And the reason for that is if we didn't do that, our matrix product wouldn't be possible. It would be ill-defined. The number of columns in a matrix that we're multiplying by another matrix, that has to be exactly the same as the number of rows in the matrix we are multiplying by. So let's suppose we only keep some number of rows, let's call it k, in our middle matrix, and we'll use this notation S sub k to describe our new middle matrix. So we end up, if we do that, using this as the total amount of space, and in the result we have three matrices, our new matrices, our new middle matrix, the result of changing our first matrix and changing our third matrix, and the total amount of space we end up using is this. So if we choose this value k carefully, we're going to take much less space than we had originally. So what are these three matrices? How do we form them? Well, to start off with, we take our original matrix and we form the result of multiplying that matrix by its transpose, the matrix that results by flipping rows and columns about. We form the matrix given by taking the transpose and multiplying that by our original matrix. So we first of all build these two new matrices. And these two matrices have some very nice properties. They are both square matrices and they are both symmetric matrices. The entry in the ith row and jth column of each is exactly the same as that in the jth row and ith column. They're symmetric matrices. And symmetric matrices have some very nice properties when we're looking at spectral analysis. One of those properties is that all of the eigenvalues of a symmetric matrix are real numbers. We don't have to be dealing with complex numbers for symmetric matrices. We look at the spectra of these matrices, this matrix and this matrix, then in effect their spectra are identical. We have the same collection of eigenvalues. So how do we form these matrices? Well, our middle matrix, it's a diagonal matrix. All of the entries apart from those going down the leading diagonal are 0, and the entries used in the leading diagonal, those are just the square root of corresponding eigenvalues for the spectra of this matrix and this matrix. Remember, these spectra are exactly the same. So our middle matrix, a diagonal matrix whose leading diagonal are just square roots of eigenvalues. What about our other two matrices? Well, we've got eigenvalues, so all we need to do for our first matrix is for the kth column, we take the corresponding eigenvector for an eigenvalue of this matrix. For our third matrix, we do the same thing, but with respect to rows, we form the rows of that matrix as eigenvectors of corresponding eigenvalues for our other matrix that we formed, the second new matrix. So how do we decide what we're going to throw away? Well, we know that our original matrix, we can recover that by multiplying our three matrices that we've described together. We also know that our middle matrix is formed from eigenvalues of this matrix. But if we have very small eigenvalues in this matrix, they're not going to make much of a difference to the final product. So we don't really need them. So to reduce space, all we do is we get rid of all but the largest values in our middle matrix. And when we've done that, that forces us to throw away the corresponding eigenvectors in our first matrix and in our second matrix that we've added, our U and our V. And what happened with our original image? Well, remember the image we had earlier with 388 rows. Suppose we look at what happens when we carry out that process with 10 rows, with 20, with 50 and 100. Well, our first effort is this. It's not absolutely brilliant. There are a lot of noise. We have these patches of red appearing. We can just about make out that this is a still life. Suppose we go to 20, it's a little bit better. The amount of noise in the image has been cut down. We have fewer of these large patches of red appearing. The central part of the image is a little bit more clearly defined, but it's still not absolutely perfect. Suppose we go up to keeping 50 rows and columns, then the result is this. This is much clearer. We have much less noise present. We've still got some. The image is much more clearly defined. It's less fuzzy than it was with our first attempt. If we go up to 100 rows and columns, then the outcome is this. Now I would say this is almost indistinguishable from the original image that we had. So this is using, instead of 388 rows and columns in our middle matrix, this is only using 100 rows and columns. So what can we conclude from that? Our last image takes up a total amount of space of 1/10 of a megabyte. Our original image took up 1/2 megabyte. Now I'm claiming there's not much difference in quality between this image and this image. The technique that I've been describing to represent a single matrix as a product of three matrices, this technique is called singular value decomposition, usually abbreviated to this. Both Python and Java provide packages which implement singular value decomposition. We do not have to write methods to carry out this process from scratch. They're already implemented. If you're interested in playing about with this, there's an implementation in Java, so you'll need this package, which is provided on the module web pages. This technique, as I've said earlier, you'll meet this again in machine learning, which is the advanced AI module in year 2, and also in data science. So the presentation that concludes what we've been looking at in spectral methods in computer science. As I said, you'll meet these again later in the program.